So this video is on the topic of directional derivative, and it is a continuing video of my previous lecture which was on the topic of introduction on vector calculus. And I talked about some basic concepts in that video, like scalar field and vector field. And I also talked about the way we differentiate or we find derivative of scalar field and vector field. And in this video I'm gonna start with the formal definition of directional derivative. So the definition: okay, so what is directional derivative? Basically it is a vector quantity associated with scalar field. Okay, and being a vector quantity, it will have a magnitude and a direction. So what will magnitude depicts? The magnitude will convey the space derivative of scalar field. Okay, and the direction of it will depict the direction of maximum change of scalar field. So I hope this all makes sense. It is a vector quantity and associated with a scalar field, and it has a magnitude and a direction. The magnitude depicts the space derivative of scalar field, and the direction will be the direction of maximum change or maximum rate of change of scalar field. Okay, so now I'm gonna define it mathematically, and for that I will consider a scalar field. So let us take a scalar field. Let fx comma y comma z be a scalar field. Okay, also I can take any kind of scalar field, like just of x and y coordinates, but I am taking this as my case. So this is my scalar field, and we have to work on the change in scalar field. Okay, so how we find we can define the change in this scalar field. We define it as del f over del x dx plus del f over del y dy plus del f over del z dz. Okay, and from this I'm gonna do some changes in this expression. So I will write it like this. So this is the first part, and this is the second part. So what I have done, these two expressions are same. This is just the dot product of, what is this? This is a displacement vector. Okay, so a displacement vector and a new vector. This is a vector quantity, this is a new vector. I will name it later a new vector. Okay, so a dot product of these two vectors is showing the change in the scalar field, or we can say that any change in scalar field can be obtained by the scalar product of these two vectors, a displacement vector and a new kind of vector. So what I'm now gonna do is to represent this whole thing with a new symbolic representation. So I will summarize this as a vector quantity and the dot product of it with a displacement vector. So this is how I can compress the above expression. And this new quantity, this new vector, is called the gradient of scalar field. Okay, so gradient is nothing but a special case of directional derivative. And what this thing is actually, if you remember, we have electric field. We study electric field and potential. Electric field and potential. Okay, and we have a relation between these two quantity as the Change in potential. Okay, the change in potential is given by the dot product of electric field with the displacement vector. That's how we define the change in potential. So this is a scalar field, and these two expressions are identical. Okay, these two. So electric field is actually a gradient of potential. That's a physical significance of a gradient of a scalar field. In the same way, we also have a gravitational field, and corresponding to that, we have a gravitational potential field. So gravitational field will be the gradient of the gravitational potential. So from here we can write as the change in the scalar field as this quantity, and the cos theta. Okay, I can bring this here, df over dr is to right, and this whole quantity is known as directional derivative. Directional derivative. We generally introduce directional derivative by the concept of gradient of a scalar field, but I have done in the reverse sense. I have considered gradient as a special case of directional derivative.